Presentation 15 was the conclusion of the fusion process, which is the pre-collection phase for your noble and precious metals, primarily gold, silver, and the platinum group metals. Now that you have that lead button, which contains all those metals, the lead needs to be separated. This process is cupellation. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Cupellation is an oxidation process with a slight twist. Oxygen from the atmosphere will be allowed to enter the muffle furnace. The lead making up the lead button is thus oxidized into litharge, which in turn 98.5% will be absorbed into the porous container referred to as a cupel, and 1.5% will be volatilized, hence the need for some personal protective gear and good ventilation. What should remain in the bottom of the cupel is what is known as a doré bead, which is a metallic alloy of your precious metals and noble metals, that is, if there are any. This bead should be hemispherical in shape, having a shiny metallic surface. It will be easily removed from the cupel, and the underside should be rough in texture due to the porous nature of the cupel. For cupellation, temperature and atmosphere need to be controlled for an efficient and complete cupellation. These pot furnaces in most cases are not equipped with pyrometers, and there is no atmospheric control. That hole in the lid will need some form of a cover. Temperature will need to be monitored by color. Experiments have been made by others. Fulton states in his papers that the alloy must be between 800 and 850 degrees centigrade, and Mostowitz states that the lead oxide melts at 840 degrees C. But Bradford says that the lead oxide melts at 906 degrees centigrade. However, it passes through a pasty stage. The point is that the cupel must maintain a temperature above the melting point of lead oxide to be able to absorb the lead oxide. The cupel must be hotter than the space around it. The extra heat comes from the oxidation reaction and other factors. Bradford in his papers state that the minimum cupellation temperature is 906 degrees centigrade, and a fellow by the name of Lodge states that for silver, along with a moderate atmospheric draft, the temperature should be between 650 and 700 degrees centigrade. More on this later. Modern muffled furnaces have atmospheric draft and temperature control features and are expensive, but for small-scale enterprisers, most will be utilizing a pot furnace as shown. The color chart can be downloaded from Google Images, as most are free as the one shown here. The cupel is undoubtedly an important factor to any efficient and complete cupellation. Cupels can be purchased in a number of varieties, sizes, and shapes. The most common is bone ash. Portland cement is commonly used for silver cupellation. There are others that are made of different refractory and corrosive materials. Those that contain magnesite will show spots of material which will allow for the absorption of lead. These cupels are not recommended, as there will be gold and silver losses. Remember that the noble and precious metals are retained in the lead. The lead must be oxidized to lead oxide and absorbed, thereby leaving the gold, silver, and any platinum group metals behind. Precious metal losses occur from the absorption of lead. Cupels can be thought of as a membrane that will permit absorption of lead oxide but will not be permeable to elemental lead. The closer that this characteristic becomes, the lesser the losses of any precious and noble metals due to absorption. If the cupel is too porous, an error in manufacturing, the greater the absorption factor will be, resulting in greater losses. On the flip side, if the cupel is too dense, a higher temperature and a longer cupellation time will be needed. This also creates losses due to volatilization. The shape of the Cupel will also cause additional losses. Flat, shallow dish-shaped Cupels expose greater surface area, which in turn allows for a faster cupellation. The problem is in the fact that it also exposes more area of the Cupel to the surface of the alloyed material, which increases loss by absorption. Porous material will absorb moisture. Therefore, any Cupel must be stored in a warm, dry environment. Moisture during cupellation is a source of spitting. One other fact, especially when it comes to bone ash Cupels, they must be stored away from acids. Any fumes will be absorbed by the Cupel. Bone ash Cupels contain calcium. When exposed to nitric acid, for example, the calcium will convert to calcium nitrate. This is another factor that results in spitting during cupellation, which equates to additional losses of the noble and precious metals. Like every other scientific method in regards to a process, there is always some form of terminology used to describe a reaction. This is the same for cupellation. It is important to preheat the Cupels prior to placing the lead buttons into them. They need or should be preheated to 850 degrees centigrade. Elemental lead melts at 326 degrees centigrade. Preheating reduces the melting time and reduces the possibility of spitting. The muffled door must be kept closed and any air inlet into the chamber must be sealed off. At about 326 degrees centigrade, a dark scum will start to form on top of the melt and eventually fully cover the molten lead. This is the lead oxide that is forming and will soon disappear in about 1 to 2 minutes, and the melt will become bright. The furnace temperature will cool down when the loading of the buttons into the Cupels is carried out. To allow the temperature to once again reach the required 850 degrees centigrade, the muffled door must remain closed. This takes about 10 minutes. The disappearance of the scum is called the uncovering, or sometimes termed the opening up of the lead button. Once the uncovering of the lead bead is completed, should be about 10 minutes, the muffled door should be opened, or the air inlets of the muffled chamber unsealed, to allow for an adequate air supply. The oxidation reaction will fully begin, and the Cupel's temperature will start to rise due to the chemical reaction taking place, producing the lead oxide. The furnace temperature must be decreased to 750 degrees centigrade to compensate for the rise in Cupel temperature and maintained. The lead button, as it is being oxidized, will take on a convex shape as the forming lead oxide flows across and down its surface, which tends to give the button a shiny, lustrous appearance. This phase is referred to as driving the lead button. As mentioned earlier, 98.5% of the lead oxide will remain as a liquid, which in turn will be absorbed into the Cupel. However, 1.5% will be volatilized. This is evident of the escaping fumes rising from the Cupels. If the process progresses correctly, and all things are going well, feather-like crystals of lead oxide will start to form around the rim of the Cupel, just above the molten lead. This is a result stemming from the sublimation of some of the volatilized lead oxide. Feathering is a good indication that the cupellation temperature is just right. During phase 3, things can and sometimes do go sour. This could become phase 4. That is, that the temperature of the Cupel drops and it is unable to absorb the litharge. If crystals of lead oxide start to form close to the molten lead button, it is an indication that the process is going sour. If the furnace temperature is not increased quickly, this litharge will start to form around the annular space between the molten button and the Cupel. This ring will start to cover the lead button and solidify, choking the button off from the oxygen in the incoming air supply. Oxidation stops even though the underlying button is still in a molten state. When this happens, the button is said to be frozen, and the final results will be low in regards to the removal of the lead. Your button, when cooled, will still be an alloy of lead and precious and noble metals. If things go well, nearing the end of the process, that alloyed bead of lead and precious metals will be reduced to the size of a pea. Oxidation decreases, and so does the Cupel's temperature. At the same time, any gold, silver, or platinum group metals that may exist will become concentrated in that small bead. The remaining lead becomes more difficult to oxidize and the remaining metals to fuse. The temperature of the furnace at this point must be increased to 900 degrees centigrade. This is done to drive off the remaining lead. If the temperature is raised too high, those remaining feathers will melt and a loss of silver will result. As the bead reduces in size, the silver becomes more concentrated and the bead more rounded in shape. Shining droplets of lead oxide will start to appear on the surface of that pea-sized bead. As the lead is depleted to lead oxide, so will the droplets disappear. During this process, the lead oxide covering the bead will become very thin and variable in thickness. The bead will appear to be revolving rapidly in the Cupel and will show a succession of rainbow colors. This interference effect of light is referred to as the play of colors. When that display of the play of colors disappears, and it will very quickly, that tiny pea-sized bead will become dull in brightness, but will, after a few seconds, become very bright and silvery in color. This bead has now been transformed from an alloy of lead and precious metals to a bright liquid globule of gold, silver, and if any, a platinum group metal or metals. This globule is now free of any oxide coating that existed. This phase is nearing the end of the cupellation process. The muffle temperature should be above the melting point of this new alloy, free of lead and other oxides. It is time to let this new bead, referred to as a door bead, cool slowly. As it solidifies, there will be some latent heat of fusion within the bead. This latent heat will cause a sudden emission or flash of light, which will also result in a considerable rise in temperature, which will last for a short period of time. This flash is the blink, and it signifies the end of the cupellation process. During the cooling phase, a lot can happen, sprouting in particular. It presents itself as a cauliflower-like growth on the top of the bead. If there was molten silver in your bead, oxygen may have become trapped. It will be expunged during the cooling phase. However, if cooling was too rapid, a solidified crust may form too quickly. The center of the bead will still be molten. The expanding oxygen will erupt through the crusty surface, similar to the gases erupting from a volcano. The material will be dislodged, splattering precious metal out of the bead, resulting in the loss. This can be mitigated by bringing your Cupel slowly towards the muffled door while simultaneously allowing the furnace and Cupels to cool. If your beads are a little larger than expected, you can place preheated Cupels on top as a lid to further slow the cooling process. One tip: if your furnace is not a pot furnace, it will have a front-loading door. At the beginning of the cupellation process, place a row of empty Cupels in front of the loaded ones. This will help maintain constant cupellation temperature, but can also be used to slow the cooling process for a more efficient cooling. When cooled, examine your beads. Your beads should be smooth and brilliant on the upper surface. They should somewhat be spherical if your beads are small. However, they will be or should be semi-spherical if your buttons are larger. The bottom of your button should have a rough texture and slightly adhere to the Cupel. This is the result of the porosity of the Cupel. If you find that the button is smooth, it will still contain lead. The finishing temperature was too low. In the end, your door bead will, if any present, contain all the gold, the silver, and the platinum group of metals. Osmium may be found at the bottom of the bead. There will always be losses during cupellation. However, they can be minimized. This is just a summary of what problems may be encountered. Temperature is a major factor. It must be controlled to some extent. Using good quality Cupels and conducting a good cupellation, losses are basically due to oxidation and absorption of the oxides. Volatilization is a small percentage, somewhere between 1 and 2%. Both of these processes are directly controlled by temperature. In general, the higher the temperature, the greater the losses, especially silver. The muffle draft is also a big one. It must be controlled one way or another. For a pot furnace, it takes a little experimentation. The air supply determines the oxidation rate. The ideal condition is 1 gram of lead converted to lead oxide per minute. Increasing the draft beyond the ideal condition generates more heat and raises the temperature, resulting in higher losses. Poor quality Cupels would either be too porous or too dense. Losses will occur as material may be absorbed. If too dense, cupellation time is increased. Both conditions equate to losses. Any Cupel on inspection prior to use, if they are badly pressed or too porous in appearance, they should not be used. Discard them. Silver is more readily oxidized than gold. Most of the losses will be in regards to the silver. Larger button size requires a longer cupellation time. This allows for the oxidation of some of the silver, which in turn will be absorbed by the Cupel. Any impurities in the button will also require a longer cupellation time, as well as an increase in temperature. Those impurities will need to be oxidized and absorbed. Loss of silver will also increase. Some gold and PGM group metals, if any, may be lost. Sprouting was discussed in the last slide. Controlled cooling is a must. The silver being oxidized is much greater than the gold. The apparent loss of any silver is not the true loss. The bead will retain some lead as well as other base metals. The apparent loss is only about 1 or 2%. Wetting is a term used to describe the molten lead spreading on the surface and the sides of the Cupel. The lead may oxidize in small patches, which will leave minute particles of silver stranded. The loss of gold can and does happen. This loss is in direct relationship to temperature. Temperature greater than 900 degrees centigrade, gold loss increases. Below this mark, losses are very low. A temperature increase will lower the surface temperature of the lead, and minute particles of the lead will become stranded, oxidized, and then absorbed. As the surface tension lowers, the lead does lose ability to hold and trap the gold as intended. However, gold loss due to absorption is reduced in the presence of silver. It has been found that a ratio of 3 parts silver to 1 part gold. The loss of gold is negligible. More on this subject in an upcoming presentation on parting and inquartation. You will encounter impurities. Some will interfere with the cupellation. Some are hard to eliminate as oxides. Loss of gold and silver is inevitable. Any antimony or arsenic, less than 2% in the bead, will not interfere with the cupellation process. However, greater amounts will form a scoria and solidify over your bead and will expand. This can even split the cupel. Any lead beads that contain antimony or arsenic should be scorified first. After cupellation, any yellow scoria formed will be lead antimonide, a result of antimony oxidizing with the lead. Bismuth is extremely difficult to remove. It oxidizes only after the lead is oxidized and absorbed as lead oxide. It remains in the lead bead after fusion and or scorification. It shows up as a yellow stain on the cupel around the bead. Due to the longer cupellation time and an increase in cupel temperature due to the oxidation reaction, silver loss is increased, and so is some of the gold. After the cupellation is complete, there will be some bismuth left in the doré bead. After parting, a higher silver count will result. Copper, as with bismuth, will also oxidize after the lead is gone. This also adds to the losses due to absorption. The doré bead will also retain some copper. Gold and silver loss will not be apparent at lower cupellation temperature. At higher temperatures, almost all of the copper can be eliminated, but gold and silver losses will occur due to the increase in absorption of the cupel. Trace amounts of copper will present itself as a green stain on the cupel, but if there is a small to moderate amount, the staining will be black and there will be minute amounts still alloyed in the doré bead. Large amounts of copper present will actually flatten the bead out, giving it a coppery color. It may even cause the bead to freeze. Cobalt, manganese, and iron will impart a red stain on the cupel, especially iron. Higher amounts will form a brown or black scoria. Trace amounts of nickel shows as green stains, but higher amounts will form a dark green scoria, which can induce freezing. Selenium and tellurium lower the lead's surface tension. It also causes wetting of the cupel, which in turn causes gold loss due to increased absorption. They also cause the bead to split up, resulting in many smaller beads in the cupel. The wetting problem may be minimized if the ratio of lead to tellurium is 80:1, and to use magnesia couples instead of bone ash. High silver count also protects the gold loss. If the 80:1 rule is applied, a lead button weighing 30 grams would be needed. For the wetting problem to occur, the bead would have to have a tellurium concentration greater than 2%. These metals will remain with the silver until the lead is oxidized. The cupel will have a pink tinge to it, but will fade during cooling. Any tellurium left trapped in the doré bead will give the bead a frosted appearance. Tin shows up as a yellow scoria, as during oxidation to tin oxide. If there is enough tin in the bead, it will choke it off from the atmosphere, causing it to freeze. Zinc, on the other hand, will burn as a greenish-white flame, forming dense white fumes of zinc oxide. This may condense on the cupel if the quantity is large enough and fully the cover of the bead, causing freezing of the bead. Your doré beads can also tell a story. Although the platinum group of metals are rare, they may exist. It is the bead shape and appearance that tells the tale. Like copper, which can flatten out your bead may be pitted or rough in texture. It could have an embossed look to it, or it may be broken into a multitude of plain surface crystals. Others, like silver, may not display itself and remain entirely as a metallic alloy in composition. If platinum is present, your bead will have a rough and frosted appearance. Palladium will present itself in a similar manner. Iridium, on the other hand, shows up as black spherical specks on the bottom of the bead. where osmium displays itself as a black spot on the bead. Rhodium has a distinct feature of crystallization, which gives the appearance of a cut gem. Ruthenium shows up as black crystalline deposits, which are firmly attached onto the edge of the bead. In this presentation, I discuss the process and some of the intricacies surrounding the reduction of the lead bead to a lead-free metallic door bead. Now that you have the metallic alloy, what next? It needs to be purified. In the next presentation, I will be discussing the process of purifying these door beads to something that resembles pure gold, at most to 3/9 fine. If you like this edited video presentation, and if you know of someone who may benefit from this information, please give it a thumbs up, a like, and a share. That's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.